possible for you to never travel your average speed. But that is not possible. So, all right. Not, at least not yet, right? Mean value theorem, blah, blah, blah. All right. So the problems, the way that they appear for mean value theorem is this. Verify the mean value theorem for x cubed, f of x equals x cubed minus 3x plus 2 on the interval -2, 2. All right, so we first have to make sure the conditions are satisfied. Do we have a continuous function on the interval? Is it a continuous function? Why? It's a polynomial. So all polynomial functions are continuous everywhere because it's a polynomial. All right. Does the derivative exist differentiable on the inside? So that's what we mean when we say the derivative exists. It's differentiable. Is it differentiable on the inside? Well, you need to know what the derivative is, right? What's the derivative of that? It's a polynomial, right? So that's going to be well behaved? Yes? When I take derivative of that, is there anything I'm going to plug in that's going to screw it up? No. So it's differentiable. So are the conditions of the mean value theorem met? Yes. So we should be able to figure it out. We should be able to find a c that lives somewhere in there that when we take derivative at c, it should equal the slope of the secant line. So here's the way we like to set these up. First of all, just take the derivative, all right? Find the derivative first. F prime of x. 3x squared minus 3. That's your derivative? Now we want, here's what we want. We want to find c such that, and I'm going to write it all down again, f prime of c equals capital F of b minus capital F of a over b minus a. And what I'm going to do is I'm going to work both sides of this down left and right. All right? So what is the derivative of the function if I plug c into it? 3c squared minus 3. Yeah? Just replacing the x with c. That's it. The right side, though, we need to figure out. Can you tell me what b is in this particular problem? What's b and what's a? It was the endpoints, right, of the interval, which I forgot what they were. What were they? It was -2 to 2? Okay, so b is what? 2, and a is -2. Understand? A is going to be the one on the left. Yes. So what is f of b? Well, that's f of 2, right? What's f of 2? We'll come in here, not to the derivative, into this. What is it? 8 minus 6. So 4. So this top left corner here is 4, isn't it? Minus, okay. Now plug in -2. When you plug -2 in here, -8. I think plus 6, plus 2, you get 0. So the top right corner is 0. Any question on where these are coming from, these numbers? over b minus a. That's 2 take away negative 2. Plus 4. Right? So this whole thing's going to be 1. B is 2. Take away negative 2, that's 2 plus 2, that's 4. So what we get here is that 3c squared minus 3 must equal 1. Solve that for c. And what do you get? Okay, so 3c squared equals 4, moving the 3 to the other side, dividing by 3, and then taking the square root. Plus or minus root 4 over 3. Do these numbers live in here? Do both of them live in there? 4 divided by 3 is about 1.3, something like that, 1.3. Square root of that's going to be, yeah, these should both live in there. So there's actually 2 points that it looks like if I graph the tangent line there, it should be parallel to the secant line. We shall see. X cubed, what was the original one? And I'm going to graph that on the interval negative 2, 2. There it is. You'll see that all right? If I connect this point to this point, right, with a line, so let me see if I forget if this can do it. Yeah, segment. I think I can do this. I'm going to go from negative 2, 0 to 2, 4. I kind of got lucky that those are easy to look at. Okay, that's my secant line, right? Connecting my 2 endpoints. If I go to positive square root of 4 over 3, can someone do that on the calculator? 4/3, take the square root. $1.15? 1.15. If I go there and I look at the slope of the tangent line, which I'm having the computer do for me, does that look parallel to the blue one? Yes. I have found where that occurs. Now that wasn't the only one. It was also at negative, right? So if I go to negative, it's up here on the top. You can see that that one runs parallel. So for this particular function, there were 2 points inside the interval where the slope of the tangent line was equivalent to the slope of the secant line, the mean value theorem. All right? Good. We'll do another one. Well, I'm not going to do any more problems. I hope that that's enough for you to get the idea of what you're supposed to do. There's not a lot of calculus in this. All you're doing is taking derivative, plugging in c, figuring out a difference quotient real quick. It's just numbers and then setting them equal. That's all you're doing. But I've got, I think, a more interesting question for you. Let me try and write it down. 2 cars on a straight track or racing. This is a closed course for safety, so I'm not promoting street racing or anything here. 2 cars on a straight track are racing, all right? Here's my picture. Here's the start line. Car A, car B. They race down the track Okay, there's the lane separating the two. They have the finish line here. Wave the flag, they go, right? Racing, racing, racing. And here's what I'm going to tell you. At the end, it's a tie. They tie. Right? They'll have to race again, but they tie. My question to you is this. There's going to be two questions. First one. Is there a speed both cars must go? I hope that makes sense. I could use the word attain. Is there a speed that they both reach, attain? Is there a speed that both cars, both of them, must attain that speed? That's the first question. The second question is there a speed? Is there a speed they both go at the same time? Not start or end. Okay, so let me explain these to make sure we're clear. I want you to think about it, and then I'll take some votes here. And you're going to have to justify your answer, all right? So you can't just be like, oh, this. I want you to kind of reason it out for me. All right. First of all, is there some speed on their speedometer that they both saw? It could be at some point in the race, one guy saw 35 miles per hour. There's another point in the race perhaps where the other guy saw 35 miles per hour. Is there some speed that they both had to see? Yes. And I'm talking about other than at the beginning and at the end, okay? Other than the start, because they're both looking down to 0, and at the end, maybe they're going the same speed, maybe they're not. Okay, so I'm not talking about the ends. Then, if whatever you think about that, is there a speed that both of them see on their speedometers at the same point in time? So is there some point in the race, not at the beginning, not at the end, is there some point in the race where they both look down and they both see the same speed on the speedometer at the same time, at the same point in time? What do y'all think? I have the biggest headache today.
I'm saying yes to the first one.
Yes to the first and no to the second?
The second one could be true, but not.
So the second one could be true, but not guaranteed to be true?
I think they're both guaranteed to be true.
You think they're both guaranteed?
Absolutely.
Okay.
Saying that they tied, I think, yeah, that the second one has to be true as well.
The fact that they tied has to be true? Anybody think that the second, I'm not going to call you out and be like, you were wrong. It's not easy. The point of this question is to try and get us to understand that there comes a point in time where your intuition can't be necessarily trusted, and we could argue for days and days upon how this would work. We need something solid to get an answer from that's unbiased. It's not an opinion, it just is this way, right? So I think there are good arguments as to why this should not be true. There's good arguments of why this should be and should not, both. But let's just take a quick show of hands. How many of you think number 1 is true? Okay. You're going to be on the herd? You're just going to follow the herd there and put your hand up because everyone else did? It's good to be skeptical, okay? You have to be willing to be wrong. I saw this really good lecture the other day, this math guy. He was doing a video on topology, which is a branch of mathematics. It's very interesting. But he was He was doing it for an audience that's not very mathematical, and it was a very good demonstration. And one of the things he was saying is, you know, what makes you a good scientist, a good mathematician, whatever it is to take a stand. Like, be prepared to be wrong. Because when you're wrong, usually you want to try and, you know, get it right, you know? But if you just sit there and you're just like, it's like a disinterest. You don't want to commit yourself to anything because you don't even want to be wrong, so you're not willing to commit, you know? It's like anything else in life. You just like don't want to actually try to do something, like you can't expect to get any result out of that. You got to be willing to fall on your face and get back up and try again. All right, so we're voting again. Number 1, true. Okay. All right, that's a majority, a strong majority. Number 2, true. We're about, well, it's not a strong majority. Number 2, how many of you feel number 2, no way that that's guaranteed? So false, for sure, false. So how about everyone else that didn't raise their hand on number 2? Don't know?
In some instances, it can be true.
Okay, so listen to my wording. Number 2, how many of you think number 2 is guaranteed to be true all the time? All the time.
Well, in this situation.
This race, but no matter how the race happens, if they start and they end tied, 2 is guaranteed. Okay? How many of you think number 2 not guaranteed? Right? That's everyone else, right? That's what I'm assuming? All right. You only have 2 choices. There's no third option here. That's actually called the law of the excluded middle. It's that we believe that statements to be true or false, there is no third, right? Yes or no, no in between. All right. How could you possibly show someone whether or not this is true? Graph?
I take mine back. I see it on the graph, like if you have 2 cars going and you're like, going at their own speed, but one of them's gonna cross when they hit the exact same speed at the same time.
So you would have to graph their speeds
Yeah.
to do that, right? That might be hard to graph their speeds if all we know is what happens at the beginning, at the end of their race. See, I can't tell you what this car A did, like how it traveled. It could have started very slow and let B get this huge lead and then just and then caught up, right? That graph would look one way, right? Or B could have slowed down and then caught up to A. Or they could have just changed places the whole way and at the end tied. So it would be pretty much impossible for me to ever graph the speed of each of these vehicles. Because it could be an infinite number of paths that it could be, right? I don't know the answer. No, I'm kidding. I know the answer, but let's get to it. All right. So this is one of those things where you use mathematics and you get a result, and whether or not you agreed or disagreed, now you have to agree with the result. All right? So here it is. It's going to use a graph, but it's going to use some other stuff too. Okay. This is time. And I'm going to say time for us 0, right? We started at 0. I'm going to call 0A, if that's all right with you. And I'm going to call the end of the match or the end of the race B. The next thing I'm going to graph are the positions of each vehicle at the end of the race. So whatever the distance is, I don't know how long that track was, would you agree that if the end of the track was here, that both of them must be at that point at the end of the race? So they both start here, they both end there. Yeah? Do you agree? Yes. Okay. Next thing, I need more than 2 colors. I need more markers. See, I have a green here. Let's see if this actually has any green in it. I'm going to use, this is going to be car A, if it works. I had a green here. Okay. Car A is going to be in green. So car A is going to do some stuff, and this is what I was saying. We don't really know what its path looked like, right? So I don't care how you draw it, all right? It's just, there it is, there, okay? You come in, change that if you want, if you don't like it. Car B I'll do in black. And I just need to connect it there to there, don't I? here to here somehow. I could do straight line. I could do like this, right? I could have even done something like this, right? It doesn't matter what the path is, right? You with me? All right, let's label these a little bit better. I'm going to call that graph, I'm going to call it F. And for B, I'm going to call that G. So this A is f of x, and this B is going to be g of x. Yeah? Any questions? These functions give you the distance and time relationship for these two vehicles. They started at the same time at the same place. They ended at the same time, same place. Yes? Now I'd like to show you that there is a point in time somewhere inside here that they were both going the same speed. Same point in time for both vehicles. All right? Guess what I'm going to use? The mean value theorem. Okay? Somehow, some way I'm going to use that. So what I'm going to do is I'm going to create a new function. All right, everyone? Here it comes. I'm going to create a new function. I'm going to call it h. Capital H, just to let you know it's special. Capital H of x, I'm going to define it to be f of x minus g of x. What I'm doing is I'm taking the difference between these two vehicles' positions, right? I'm taking the f, subtracting the g, and h would measure the distance between them, wouldn't it? I'm creating this new function. Does everyone agree that that right there, h is still a continuous function? Yes? Because f and g were continuous, or else these cars would be magically going from one spot to the next without actually traveling through space, right? These are nice continuous curves. So h is continuous on AB. Is h differentiable on the inside? Well, as long as these car paths didn't have any corners, then when I put them together with subtraction, they should still not have any corners. So if you take two differentiable functions and subtract them, it's still differentiable. So this should be good. You agree? So I have a continuous function on a closed interval, I have a differentiable function on a closed interval, and I've got this. I know what h of b is. What's h of b? Well, by definition, it's what? F of b minus g of b? But that should be what? 0, right? And what's h of a? 0 also, for the same reason, right? By the mean value theorem, there exists a C inside AB, right? That's what the theorem says. There's some number inside the interval such that what's true? I'm working with capital H here. Such that what's true? The derivative of H at C, right, must equal the slope of the secant line connecting the endpoints of H. Does that look familiar? It's the mean value theorem, but I'm working on capital H instead of little f. Because H was a continuous function on a closed interval and it was differentiable on the inside, right? Now, the reason I showed you this is because what does the right side of this turn into? What's the top here? 0, right? 0? So that means that the derivative at some point C is 0, right? We're almost there. Actually, we're really close. That's just what the mean value theorem says. Let me remind you, what was h of x? What was h of x? It was f of x minus g of x, right? That's the way I defined it. If I asked you right now to take the derivative, you would say that the derivative of this is equal to the derivative of this side. What's the derivative of this side? No, just the derivative. If you have two things subtracted, how do you take derivatives? Derivative of each one? Right? That's what that would be. Do you agree? So if I tell you that at some point the derivative of h is 0, isn't that equivalent to me saying this? H prime of c equals f prime of c minus g prime of c, that equals 0 somewhere? Yes? So that's saying that f prime of c minus g prime of c equals 0. Does anyone see what I can do right now with this? I'm so close to being there, but I'm not trying to just throw it into your face. I want someone to see it. That's right. This is saying exactly that f prime of c must equal g prime of c. Right? That's what that's saying? Isn't that exactly what we were trying to show? If I take two graphs, f and g, I tried to find a point c where their derivatives were equal. The derivative is the speed, isn't it? If it's distance and time, derivative is speed. So what we've shown is that there exists some point c. The c lives somewhere inside here where the slopes of the tangent lines are equal, which means that the speeds are equal, which means the speedometers were the same at the same point in time. That's all. This is what I needed to show right there.
Is there a way to find that point?
I would need to know the actual functions. I would need to know the function of the path of the car. So there's no arguing it, unless you want to argue with the mean value theorem, but that's been proven already, so there's not really much to argue with there. Say again?
You answered the second question.
The first one is now true also, because the first question didn't require it to be the same point in time, right? So that one's answered. If these two cars start at the same spot and end at the same spot, right, then they both have the same average speed, don't they? And we already know that by the mean value theorem, each car individually must travel its average speed individually. What this is saying, be careful here, this does not say that their average speed is the speed that they must travel at the same point in time. That's a totally different, I don't know if you follow that? Like, you sure?
So the second one's false then?
No, they're both true. They're both true. Look, if we both leave San Antonio and arrive in Austin at the same time, then we both had the same average speed. And we already said that if you drive from here to Austin, you have to at some point in time go your average speed. Yes? So we both reach our average speed somewhere. Was it the same point in time? Not guaranteed, right? The second part says, but was there a point in time where both of us did travel the same speed? Not the average speed, but the same speed. That speed, I don't know what it is. I would have to know the function first. What's that? I thought I heard a comment.
I thought you were talking about the average speed.
Okay. Oh, and the second one?
Yeah.
Okay.
That's what I
Yeah.
thought.
Okay. Yeah, this problem takes a little while to get your head around because you have to be careful. Are we talking about the average speed or like just a speed somewhere in there? But it's the actual working of this proof. Like how many of you would naturally say, hey, I'm going to define a new function h of x to be the difference of these two functions? That's not very natural, right? And for those people who are going to do a lot more analysis of functions and just things like this, coming up with this is just part of the game. It's just you try something and works, and it's hard to appreciate. All right, I'm done. Let's see, homework for this. I'm only going to give you a few problems. You're going to finish off the 4.1 homework. I would encourage you again to go back and look at evens for 4.1. In 4.2, 9, I'll tell you the page in a second. 9 through 12. This is off page 215. Now, they don't give you a whole lot of these to practice. I don't like that, but this 9 through 12, and I already did one. So that's it for this section. All right?
Do you have any practice on that, like on Canvas?
Do what?
Do you have any practice problems
On Canvas, I don't think I have anything else. Just Google up, practice, mean value theorem problems or something. I'm sure there's something out there. I think you're free to go. I have such a pounding headache right now, I'm losing my train of thought. Yeah, that's it.